This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
This is Paul Verschure with the Convergent Science Network podcast. And today I'm with Marc Toussaint, who's a speaker in our summer school. And Marc, as a physicist, has been presenting his important work in the domain of machine learning. So Marc, you started your presentation with like a little test for your audience where you showed them a few equations and you want to check out who in the audience would recognize these equations. So why were these equations so important to you?
Well, first, just to check like what kind of background people have. I'm not so sure if they're so important, but I think they are important to eventually understand, what the point is of these formulations that I presented, and to sort of understand that, the third equation on that slide is something that we can get out of these new formulations.
Mm-hmm. Okay. And actually, I think you looked a bit disappointed because it was not a large group of people who immediately jumped up like, yes, I know this one. So,
yeah, there is something. Reinforcement learning is a very, very basic model of how behavior could be organized and how behavior could be organized in a way that is goal-directed. Mm-hmm. And although, there's many, many questions whether this helps you understanding the brain. Of course, there's many questions. But still, this should not, free you of knowing these things. Mm-hmm. I think it would be good to teach them. Yeah,
absolutely. Now, what you initially emphasized were your methods for, let's say, to understand planning as a form of inference.
Yeah.
So, why do you think that that's a useful way to think about planning?
First, it's an alternative way to think about planning, which is a good thing in itself. I think, turning over problems and looking at the same problems from different perspectives is important. I think the perspective of looking at planning from the perspective of planning, offers different, options of how to think about a computation that actually realizes planning. So more concretely about why planning is inference, I think it does allow you to be creative, to use other kind of computational algorithms that exploit different types of structures. To be more concrete, if you think about how to do planning on factor representations, well, one way of thinking, the more classical one, would be to have structured representations of the value function, but it will always be the value function, right? Whereas if you roll out that process and sort of formalize it as the whole model as a graphical model, and show that inference in a graphical model can solve planning problems, it really leads to different types of algorithms and different types of, approximations that you could use to solve planning.
But would that mean you really have removed the value function from the story, or you have redefined it?
That's also very interesting. That's a good question. So I have removed it in the computational algorithm itself, so that the algorithm does not have to have explicitly a representation of the value function in its memory, or the computer doesn't have to. But in some cases, in particular on normal Markov decision processes, the algorithm will compute things which are one-to-one to the value function. So for instance, on normal Markov decision processes, the backward messages, it's getting technical, but if you sort of collapse them, they are equivalent to the value function. Mm-hmm. But again, now all of this is only true on a normal Markov decision process. If you go to problems, the actually interesting problems where you cannot do exact inference or exact value iteration, like in POMDPs or other kind of factored things, the messages do not anymore correspond to value functions. They really correspond to probabilistic posteriors. And it would be unclear how to do the same things that it could do with inference, how you could do the same things with value functions.
Mm-hmm. Right. So in that sense, also if you go to the Bellman equation view, which would be more dominated by a value function, then for you this is also, let's say, a contrast, right? You say, okay, that's one way to look at planning.
Yes.
And you want to look at alternative models to solve it. That might be more simple, or are they just different formulations of the Bellman view?
they are different. I think they're different to the Bellman view. So the Bellman view is really the Bellman equation is a backward thinking. So if you have already solved a small problem, you can sort of backward iterate and sort of move your horizon backward and solve the larger problem and so forth. So in the Bellman view, it's not very symmetric. It doesn't think about, for instance, forward messages or forward information. The inference view does. It computes both forward and backward messages. And the result is then a product of both of these being the posterior. So I think it is a different view than the Bellman view. Yes.
But I could argue that I might, let's say, describe your inference-based approach in terms of a Bellman equation. I can show an equivalence, or is there really something missing?
I don't think that the computational things that are happening during message passing, you could describe as being a form of Bellman equation. So computationally, the things that are being computed and the kind of messages that are being computed are different.
As a result, they will also solve somewhat different problems.
Well, they lend to different approximations. For instance, as I said, in a POMD piece, in POMD piece, sometimes you can do exact inference as well. But if you do message passing, you can cope differently with large problems or with factor problems as you could do with trying to approximate value functions and iterate over them.
Right. So now you mentioned that's sort of introductory remarks, but you mentioned that on the one hand, you found problem solving from the perspective of inference theoretically interesting, but also you said, look, it can give us a handle on a more large scale integration and possibly on some form of multidisciplinary interaction.
Right.
So what's the perspective there exactly?
So I think generally actually probabilistic modeling and also graphical models, there's two things about them. So some people say they're great tools because they work good, but another thing to say about them would be they're nice because they offer one nice language that can be applied on many different disciplines. So graphical models can be used in linguistics, in robotics, for inference, for whatever. It's a bit of a similar thing that I wanted to state with planning as inference. The first point to make is that it's one language that allows you to talk coherently about both decision making, doing perceptual inference, sensor processing, also planning. So not only immediate decision making, but also planning in one coherent set of concepts. And it's actually a rather small set of concepts, just inference, right? I think this is good for communication between disciplines. That's really one point. And as I said, one example of that is that having these concepts that you can show that they explain planning or other things allows to build bridges between disciplines. As I said, there is neuroscientists, and I don't have an own opinion, but there is neuroscientists who like to argue that neurocomputation can be abstracted as functionally doing something as Bayesian inference, or to say it even weaker, that neurosystems could at least also realize something as Bayesian inference. But that is an interesting statement, because if now in other fields we can show that Bayesian inference can solve planning problems, we immediately have a hypothesis of how neurosystems could solve planning problems.
But is it also a goal for in your own work? Is it?
I wouldn't really say so. So particularly in the last years, more and more I became more and more of a roboticist, really. And so in a positive sense, yes, I am inspired, and I'm inspired by the questions of how actual systems like the brain can solve problems of goal-directed behavior, manipulation, all of these things. But it would be too much to say that I myself see myself as a researcher, like a brain researcher.
Right. Okay. So then, let's say the approach that you have great confidence in at this point in time is what you call stochastic optimal control,
which is a problem definition, not an approach. Yeah.
So, but why do you think this is an important set of problems then to deal with?
And that's again a good question. So let me say what I guess many people would other people would say, right? The stochastic optimal control is a problem definition similar to Markov decision processes with reward. And it's a very general one. People like when things are being formulated general and problems being formulated general, and allows to sort of, describe all kinds of planning problems in there. And it's of course, accepted within the control theory itself. And it's quite a lot of work on within machine learning in terms of Markov decision processes.
Mm-hmm.
Let me put it the other way. If I would not have shown and embedded my theory to be important or useful for solving MDPs and optimal control, I could have not convinced the whole control theory community or machine learning community that it's worth anything.
Okay.
Right?
So how did you then solve this problem?
Solve which problem?
Well, in stochastic optimal control. Right? So you were saying, look, you tried to show that your framework is applicable in that domain. So,
exactly.
So in that sense, I guess you want to have an impact that sort of also delineates your proposal from others. So what are the unique features of what you proposed in that context? Why did it work better, or why was it more appreciated than alternatives?
Right. One of the achievements, I think, is a theoretical achievement in the sense that we could show that many, many other algorithms, which themselves have, proven also, empirically that they work well, that there are special cases of the formulation that we have. So this is a purely theoretical statement, right? Algorithms 1 to 10 are special cases of the framework.
Right.
And algorithms 1 to 10 had done some effort, fortunately for us, already to show that they're computationally okay. So that's one thing. The other thing is that we could also derive one algorithm, which is the model-free reinforcement learning algorithm that I find conceptually quite interesting, in that we could also, directly compare it to other algorithms.
But if we now first look at the first part of this argument, where you say, well, we had the most fundamental formulation of a solution to this set of problems. What are the key ingredients of that solution?
I'd say that the key ingredients have already previously been formulated by people like Kappen and operand. So the key ingredients is to think about optimal control as formally it's a Kabel-Gleitner minimization problem, but matching two different distributions, the one being the controlled one and the other one being the uncontrolled but conditioned one. So these key ideas have previously actually already been formulated. And I must say, it's also not, you could even go back and talk about Kalman duality in general. Even Kalman already like said that the problems of control and the problems of filtering, like state estimation or Bayesian filters, are very similar, right? And what Bert Kappen did before us, and we now also do, just explicates exactly that relation, makes it explicit. Now, that difference in the formulation is really that we're talking about processes over state control and not really making any assumptions about the dynamics or control costs or noise in the process. Whereas the previous formulations, they discuss processes on the state, and for that reason had to do some special assumptions to actually, get the theory properly.
So you in some sense, you had a more reduced formulation of the problem. You just left out a certain number of aspects that you saw as being irrelevant, really, to the solution. You could
put it like this. Yeah.
So now, how should I imagine the solution that you came up with for these kinds of problems? How does this problem solver really operate?
I think most concretely, you could imagine it, in terms of that policy that I described, which is actually described by Boltzmann energy. So you actually have a policy which is represented via Boltzmann energy, which is not really any assumption about the policy, because any conditional distribution can be represented as a Boltzmann distribution. And then the iterative solutions that we proposed translate to iterative updates of that Boltzmann energy. So concretely, I should say that these iterative equations are actually equations which perform that Carbon-Gleibler minimization that originally the theory proposes should be done. So these updates of the Boltzmann energy are concretely the argument that has to be implemented eventually.
Right, but now basically it means I have a set of policies over which I want to optimize, right? They all have their own level, their Boltzmann energy attached to it, right? And now you're going to update these iteratively. So that means that you are sampling from some set of states that might describe the task that this policy has to be applied to. So to get this iterative function to work reliably, what should be the properties of the states I'm sampling over? Can it just follow any distribution, or should it be very regular?
So first, I wouldn't say that we have a set of policies, but just one, but being described by a distribution. In the exact update, where we assume we have a model, we update that Boltzmann energy over the whole space of points. So the whole function we update over for all x, for all states. That is the model-based case, or the stochastic optimum control case, where we assume to have a model. I think what you refer to is when you ask, but for which states do I update it, or which states do I have to sample? This is the model-free case, right, where the system really has to interact with an environment. Well, in that case, the system would have to unroll episodes of experience with the environment. And these episodes of experience give you, samples from the process. And you can use these samples of the process, as a standard, also with TD and Q-learning and so forth, to do the necessary update of the Boltzmann energy in a stochastic way. So with a learning rate alpha, instead of doing the exact update of the energy.
Okay. But then, so the point is, what I'm looking for, what are the boundaries on that solution, right? So not only to formulate the solution, but then to prove that it actually will work and converge, you do have to make assumptions about the space in which this algorithm operates, right? So what would be these limiting factors?
Let me think. The first one is we only considered observable environments. So there is no partial observability in what we discussed. And I wouldn't really know yet how it would transfer to partially observable environments. A second thing, I think, in terms of the when we can do these updates exactly, I think we proved convergence without any further assumptions, right? So these iterates, they converge. We prove convergence without further assumptions. But this is true if the updates are exact of the energy. So how, under what circumstances can it be exact? It can be exact if the state and control space is discrete, because then we can represent the energy just as tables over discrete states and actions. In that case, it will converge, no assumptions. If the state space is continuous or otherwise, has to be encoded more compactly, the convergence is, more difficult. If in a continuous case, actually the dynamics is so simple, for instance, just linear and quadratic costs, then you can just make a quadratic assumption about that energy, and it's almost like the Riccati equations and so forth. You can do the updates exactly, and again, it will work. If the dynamics is nonlinear, you would have to use a function approximation to represent that energy. And at that point, exactly, we lose that strict convergence proof.
Right. Okay.
And can only hope, really, as so often with reinforcement learning and the function approximation.
Right. So then the other thing, and sorry if you want a trick that you applied in this approach, that you in some sense, let's say, completely fragmented your value function, right? Because you now added a variable to your system that was locally linked to every state. That is now the reward function that relates to that state. And if I understood it correctly, these reward functions do have to satisfy certain regularities for the system to operate correctly, or not. What's the price you pay by distributing your value function in this way?
I'm not sure. I mean, these reward functions, we didn't really put assumptions on them.
Right.
except perhaps for a convergence that they are bounded,
Right.
as also for Q-learning. So to prove convergence of Q-learning, you would have assumed that they're bounded, but otherwise there's not really constraints.
But the point was that in some sense, you also contrasting again with this Bellman perspective, where you would have an explicitly defined value function, right? In this case, you have a more implicit defined, it seems, value function, or not.
I wouldn't call it value function. We have the rewards and we have the Boltzmann distribution. Nothing more.
But you could argue that in iterating these distributed value states, you are approximating something like a value function.
In iterating the update of the Bellman, not the Bellman, the Boltzmann energy.
So what I'm after is just to say that you seem to draw a distinction between a value-based approach and your approach where you say it's not value-based in some sense. Well, I'm saying, but maybe implicitly you are value-based but now you just have sort of hidden it more by sort of putting a distributed in the system linked to every single state.
Yeah. So first, yes, the relations in the end become very close. I'll elaborate in a second. But the distinction is not so much between, or I didn't meant to initially distinguish between a value-based approach and our approach, but more like an approach which computes value functions by iterating back the Bellman equation versus by computing other things in terms of probabilistic inference, right? So the Boltzmann energies are eventually computed minimizing coupled-Labler divergences. Fine. In the model-free case, I derived that one equation like that, the model-free reinforcement learning equation. And you can analyze the fixed point properties of that equation. I should emphasize it's the fixed point properties, right? It's not the transient of the learning process itself. In that fixed point, this Boltzmann energy has very interesting properties. Set for non-optimal actions, it goes to minus infinity, making these actions very improbable to be chosen in terms of action selection. For the other ones, it turns out in the fixed point, for optimal actions, it corresponds to the optimal value function, the Boltzmann energy, which is surprising, but it's actually a simple outcome of, analyzing the fixed point equation of the update.
But now the other thing that was interesting in the approach you described is that you very strongly relied on the inference component, also with respect to sort of looking at the consequences of future states that the system might anticipate onto its priors, right? That you sort of, as you described yourself, as if you just imagine a future goal and then suddenly you just pretend actually you have achieved it and you look at the consequences that has on the system. So what's that dynamic exactly, and why did you approach it in these terms?
I mean, don't quite understand what you mean by dynamic. I mean, it's a bit like
it's dynamic because I have to now imagine a future state. I may now include it in my priors, and now I can make decisions on that basis. So I can propagate myself now to future new events, right? And I can go through that same loop again.
Right. So you imagine future events as happening, right? You condition on them and compute a posterior. And in the last framework, you do iterate by using that posterior again as a prior, and condition that again on the same future event, and again compute a posterior. Right. I mean,
but do you consider that problematic or not?
I don't. Algorithmic wise, I don't see why it's problematic. Do you mean problematic in terms of interpreting how, I don't know, living systems are doing it? Or?
Well, from to me, it seems that this works because you have conditioned it on a very specific definition of the problem domain, right? So, for instance, that I can only have single goals existing at any one point in time, as an example.
No.
Why not?
No. You can arbitrarily condition your future. There can be many. The future can be represented in a factored way. You can have goals in different representations at different points in times.
No, but wait, you might have, if you now propagate that back into your priors, you might have, let's say, unexpected conflicts between these goals that you do have to resolve now in some way.
So inference in graphical models, if there is evidences in a graphical model which are inconsistent, the likelihood is just zero of that thing, and the messages diverge, and that might in fact happen, and that happens in graphical models if there is like almost deterministic dependencies, and you get these really inconsistencies. So that's the case when you condition on variables which are observations which are totally inconsistent. If there is a chance, the slightest chance of consistency, inference will exactly, generate a compromise. That's the point of it, right?
Yes.
So, if you have deterministic models of our future and we condition on too many things, it will diverge in a sense. Otherwise, it just behaves as inference in graphical models.
Right. But then, so in some sense, that means I just get points in this graph structure that have lost their validity. I will just not consider them anymore, and I rely on others then to make my decision.
Don't know. So, I mean, inference in graphical models wouldn't really do that, right? It would find a compromise in a probabilistic sense. Right.
Another constraint I was worried about is just time.
Yeah.
Like, for instance, if you also mentioned that you have an interest in mapping this to robotics, and if you deal with robots, the key thing is real world, real time. So, for instance, goal setting might also evolve over different time windows, right? Or I might get, let's say, goal interrupts because the world interferes with my own ideal planning world.
Absolutely, yeah.
So I was wondering how your solution would take these kinds of let's call them exceptions into account, or how robust it would be in the face of that.
So we don't know if we have so much experience. Certainly we used that planning as inference method for models that are related to relational reinforcement learning. I didn't talk about this yet. And these are like relational models on a symbolic level. And, can describe problems like, should I grasp this object or manipulate this object to achieve a goal or to build a tower or things like that? Do I first have to open a door before I get an object and all these kind of things? So we use these models and planning as inference in these kind of models, which is really fast, really, because it's on a symbolic level, very fast compared to all the low level motion, stuff. So, in those cases, what you call interrupts or unexpected events or things like that, would just require to sort of redo the whole inference, which, because it's on a symbolic level, is really very quick. So I don't know, currently in practice in robotics, I'd say, the inference is so fast that, you just update online all the time.
So, okay. So you're saying this will just be equalized out by compute speed. This is
you could put it like that, yeah. By just having the system to just update itself and recompute the posterior whenever some new evidence comes in.
Right. So then also at some point in your presentation, you gave a little scheme where you distinguished different variations of problem solving approaches, like model based versus model free approaches.
That one.
Right? So what's that structure that you had exactly in mind there? How does it organize the different approaches that are around?
I didn't really think that there's like one structure which combines all these approaches. I mean, that diagram was just to sort of give an overview of what kind of approaches people follow in reinforcement learning, right? So model-based, the path going over first learning transition models, and model-free, just learning value functions. I mean, Dyna, which combines the two in one framework. I don't know. So our own work is mostly, actually the work that we use in robotics, which I didn't talk much about today, is really fully model-based. So we always actually follow model-based approaches. And it's only in that, what I talked about today, in that more recent work, that we came up with a model-free reinforcement learning algorithm, which I find interesting for other reasons. But in robotics, I must say I'm more a model-based proponent.
Why is that? Why do you find that more interesting or relevant?
In particular, for the types of problems that we did in relational reinforcement learning, where the state space is inherently exponential in the number of objects. So the state is described by all the relations between objects. So if you have 10 objects, there is on the order of 10 squared binary relations between them. All of them can have a value. So your state space is, say, 2 to. So the state space is exponential in those cases. And how do you do learning in these kinds of spaces? And there's model-free approaches as well, who sort of represent also the policy directly on some relational features, so first-order logic features, and then use policy gradients to actually optimize them. But we think that the generalization is actually much stronger if you try to learn models from the experiences. And the models in those cases are represented by stochastic relational rules, almost a bit like strip, but they're stochastic in their first order. And it's not our own work. We use that work to learn these rules, and we find it fascinating how strongly they generalize. So from only a couple of experiences that something rolls when you push it, the robot generalizes quite, rationally, one could say, quite interestingly to other objects and so forth. So it is what I find interesting about model-based approaches is the ability to generalize experience. But the problem of model-based, of course, is, well, now you have that nice model, but how do you translate it to actions? And this is where then the planning as inference comes
right, exactly. In. But to what extent are these models actively acquired?
Nice work. So the last 2 years or so, we've been actually investigating a lot in active exploration or active learning. So where systems should decide on actions that maximize information gain. There's the theory of active learning in machine learning, right? So one of the questions we had is how can we sort of transfer these methods, the existing methods, on the relational reinforcement learning, and that requires that estimating information gain or estimating your uncertainty of predictions, as it is done in also implicitly in Rmax or the Bayesian exploration bonus, how to do the same thing with stochastic rules. And we did that. We call this relational exploration. And that means that, if the robot has observed a ball rolling, a green ball rolling, and then a blue ball rolling, then it maybe would not be interested anymore in another yellow ball, but instead try to roll something which looks different to balls, right? So, absolutely. So these are exploration strategies that we investigated and which are really important in these exponential state spaces to lead to efficient learning.
Right. So, but for you, the main difference is that you say, look, if this state space gets too large, you just need a better strategy to map it, and that's an active learning, or an active exploration component. While intrinsically, you don't need to change your whole approach. It's just the way how you explore that state space.
I agree. So intrinsically. It's a funny choice of word because of intrinsic motivation, but it's the same principle. So it's still the same principle of maximizing information gain, which is approximated as it is in Rmax or Bayesian exploration bonus. What is necessary is to transfer that same intrinsic principle to other types of representations, namely those relational representations or these stochastic rules we had.
Would you think this game would change a lot when I would impose a memory capacity constraint?
Don't know. You mean the exploration strategy would change?
Yeah, or the whole model construction phase.
Well, in the model construction, there's a regularization penalizing the size of the model. So putting a hard limit on the model sometimes can be even shown to be sort of dual to actually regularization. But yeah, I'm not sure if it would change.
So why this is interesting to me is, look, I try to understand how the brain works, and the brain just doesn't have these luxuries of infinite memory or infinitely fast processing speeds and so on. And so this, of course, raises this issue that maybe the brain is operating in a part of problem-solving state space where we just are not really looking with our algorithms because we're not looking at the same constraints. So it's for that I'm asking, look, if I take a constraint now, let's say memory capacity, would that change the game from your perspective?
I'd say I don't know if I can say anything to that. I have the impression that the kind of models that we learn are so small compared to the things that humans really learn. Humans would have much more capacity than what our models that use these stochastic relational rules, for instance. Right. Actually, I find it sometimes quite surprising how much humans can memorize, children especially, without actually abstracting, just as if they would just store it away before they actually
without
later
being
on
programmed by you. It's amazing.
Yes.
No, but so the other thing here is also, for instance, a lot of these methods that are very advanced, and you guys have a deep understanding of them, but they are very often predicated on fairly strong assumptions. For instance, one thing that I find often worrisome is that, for instance, people sort of very loosely say, well, okay, let's assume I have defined my state space, and now on the basis of that, I'm going to show you all sorts of properties of my algorithm, or I'm going to learn a model, I'm going to do problems of, and so on. Isn't that assumption actually too strong? Shouldn't we also think more about policy learning together with really the state space acquisition from experience?
Yeah, totally agree. Yes, I totally agree. I mean, the question of where the representations comes from is absolutely fundamental. Maybe there is two ways to go about this. So the one is really having the ambition that the system should really invent its own notions of state, its own representations and everything from scratch, which has been the ambition for some while, right, by researchers, and ideally even under partial observability and so forth. Which even myself, I was thinking about that, but more and more, I think this is very tough. Still, we should still continue trying, right? The more I actually work with robotics, the more I have the impression that it might be worth, before trying to invent algorithms that can invent representations for, all possible worlds, to actually understand that actually our world, our 3D world, is quite special. And it's special in the sense that it's 3D, there is physics. A lot of things in our world are actually about rigid bodies. It's becoming now very robotics talk, right? There's a lot of things about really kinematics. So there's degrees of freedom in our environment that we can manipulate and so forth. So our actually true world is very, very structured. So in that sense, why not, as a simple step, because we're limited as researchers, as humans, first try to understand, those particular structures that are inherent in our world, and think about what would be representations to actually deal with those. So that's also a more robotics-like pragmatic approach.
But it's also funny that you're sort of following a little bit your physics training or intuitions again by saying, oh no, let's make the spherical cow, and then we start from there.
Frankly, I'm not sure. I think it's the opposite in physics and training. I think the typical physicist would go the first approach because he wants to be always general and work in every possible world and derive optimal solutions every possible world. And in a sense, also machine learning and optimal control and MDPs, they do that, right? They define problems which are seemingly total generally because you can describe everything as an MDP or a control problem, right? And you can embed everything in a vector space, which is sort of true. But it might neglect the fact that the actual problems we are faced with are very structured. And acknowledging that specific structure is maybe, it's maybe less a theoretical physicist thing, but more really in engineering and robotics.
Okay. But do you feel that there are already solutions of that kind on the table?
No. Looking more and more into robotics, I think that, that there is, of course, there is engineering, which means that the people who program the roboticists, they have these concepts and these specific representations and understanding of kinematics of worlds and so forth, and from their understanding, then program the robot to deal with that. But I do not have the impression that the machines themselves, so let's say the inference mechanism in the models that I talked about today, that they would actually do inferences about true physical situations.
Right.
Or that we would have inference machines which could do inferences about what is a stable physical situation, like probabilistic inference over that, or where might be a degree of freedom in the world. This is so doing inferences in this spaces, they're so structured that I think we do not yet know how we could do probabilistic inference in those phases.
Right. So what would be a good benchmark for these kinds of models?
Okay, so there is the old Köhler, Wolfgang Köhler, right? He was a what was he? Psychologist, beginning of the 20th century. Did these experiments with monkeys,
chimpanzees, yeah, famous.
Exactly. I loved them on which island? I forgot. So he has this book which is called Intelligence Tests of Apes, something like that. And in these books, he describes actually very nice behaviors, which I would call really goal-directed behaviors. And one of these behaviors is where there is a banana at the ceiling, and the robot's trying to get it, but it's too high.
No, it's a chimpanzee who tries to get it, not a robot.
Oh, sorry. you see where I'm getting at, right?
Yeah,
These would be the tests. The ape wants to get it. It's too high. He jumps, and for 5 minutes doesn't achieve it. Gets sort of depressed. At least that's the storytelling that Köhler actually does in the book. Sits in the corner, sort of depressed for a while. And then suddenly points its eyes towards the banana, and then points its eyes at the box in the corner, and then again at the banana and the box, and then jumps up, grabs the box, goes on top of the box, and gets it. And I wish, robots could do that. Okay. And I think if I would be a psychologist or so, I would be very interested to actually model what's going on in that head of the monkey, because I think he did inference in a very structured way, inference about our physical world. He did inference about, let me pull that box here and get on top of that. Right. Exactly. And it's exploiting physics very, very much. Yeah.
Yeah, we had a beautiful lecture on this last week by Alex Kaczelnik, exactly on this famous experiment by Köhler, with also many other experiments in that domain. Great. So you would stick to such a benchmark. You'd be happy with that.
Absolutely. If the robots would do that, I'd be
very good. But now I don't know if whether you guys ever apply your own methods in an autobiographical way, because you could also say, look, every machine learning person is trying to optimize their own policy in this complex world, and in some sense, we also would like to make statements about biological systems, about physical, psychological systems, and so on using these methods. But there might be a possibility that of course, you guys have optimized yourself in some sort of local minima in this larger space of all possible policies and problem-solving solutions, that actually the links with natural systems has gotten lost. Okay? So where do you stand on that? To what extent also the models we now, very superficially discussed now in this interview, where is really the leverage, right? Because, for instance, we all know the big hype that has been going around and the big enthusiasm and hope for the last 30 years on these kinds of methods. And in some sense, when we look back, we can also, it kept a lot of people busy. That's all very positive. But did we really sort of make a huge step forward in understanding biological systems or psychological systems? And there, it's not so clear, right?
Yeah. I agree that there is not necessarily always links to the biological system of the methods. And I would even claim that's very often not the goal, to keep these links to the biological paradigm.
Well, why not?
It can be one goal for some people, but right, it's also feasible. An engineering goal really to just design systems which do things good in a good way, optimize something or whatever. But let me put it the other way. I think in order to understand living systems, it is also a good idea to understand our world, our environment, and to understand what it means to behave, or to organize behavior in that environment. Totally, just on that level, like I tend to say functional also, without caring for the substrate, without caring for, the constraints, the concrete biological constraints that there are, but just to understand what is actually the structure of problems that things in the world are being faced with, right, no matter if these are robots or not, or other systems. And I think that the engineering methods or robotics can contribute on that side. And I also think that, it's important to understand actually the problems when you then would go back and ask, how could biological systems actually face these problems?
So it's a bit more a normative perspective then. Like this is what the system should do.
Should do is even too much. What the system is confronted with. Understand the structure of what it is confronted with, really.
But now, if we look at nature or psychology, we might see that actually notions of optimality might not hold so well, right? Like human decision making is in many occasions suboptimal. I'm here wasting your time, and you're still being polite, so you could also consider that suboptimal, right? So in the face of, let's say, psychological reality and behavioral reality, how do these notions of optimality then actually hold up to that?
Optimality. So I have a very pragmatic, actually, relation to optimality. I think many empirical things can be described as if they would adhere optimality principles, and it's a misunderstanding to actually say that this would have any meaning, like if it wants to be optimal or whatever. Let me take an example. I mean, the trajectory of a particle in physics, right? You can say it minimizes action, or if I don't know, some kind of field in physics, it behaves as if it would minimize an energy. That energy or that action, this is only a scientific concept that we scientists have devised to describe the actual system there, right? So by which I'm saying cost functions or optimality objectives, like these things. These are just designed by us scientists to describe systems in the world. It's just a means to describe systems in the world, to say the system behaves as if it is optimal. So I think it's a misunderstanding to really think that we believe machines must be optimal. It's just a scientific tool to describe them as being optimal with respect to some arbitrary cost function.
But for instance, humans have many biases in their decision making, right? And there's some beautiful books written about that. One might be, for instance, many people in gambling believe they have much more control over the outcome of a bet than they really have. So they see in psychological reality, you might not be able to really optimize so cleanly on some goal function, even though that is really at the core of the methods that you're developing.
No, I think, and this is almost a trivial statement, that any behavior can be described as being optimal. It's just a question of optimal with respect to what. So, I mean this, and I mean it's no more statement when I'm saying I'm interested in describing algorithms that can do optimal things. It's only that I think that this is an abstraction of how to describe behavior. I think even what people call sub-rational behavior or limited behavior, of course, you can describe it as being optimal with respect to something, some other objective.
Okay, but then of course there's another risk that's looming, another challenge. That I could say, but in that case, your method is super powerful because it can never fail. So then what do we learn?
Well, the thing is that you now sort of shifted your level of scientific description. You do not describe behavior, phenomena directly anymore in a direct representation in terms of describing a policy, but you shifted your level of scientific description to the level of describing what they optimize. And at first sight, it's nothing more than just a shift. You didn't gain anything by that. But the potential what you could gain is that this other description is more compact. And that's really the only scientific gain of that you can describe things more compactly. And this is, how it was in physics always. The reason why you would want to describe particles as minimizing action, so the trajectory of particles, or so, is because it's a very concise description of what's happening. I mean, alternatively, you could just write down for every possible thing what happened, right? But it's more concise to describe like that. Same with, behavior, like human motion, saying that human motion, as in Walpott's work, behaves as if it would be stochastically optimal control. Don't overstate this. It's not meaning that they want to optimize it or so. It's just a statement that you can shift your scientific description of human behavior onto an abstraction, where you say the motion is as if it would minimize that objective function.
Right.
Just a shift of description, nothing more.
And a description of it, right?
Right. Yeah. The hope would be that it's so concise that, for instance, with robots, it's easier to specify or be creative in saying what they might want to optimize, and then derive behavior from that, rather than programming behavior directly. It's a shift of programming languages, almost, if you want to say. Now we're programming objective functions instead of policies directly.
Right, exactly. So, Mark, you're deeply involved in developing these sort of also new perspectives on problem solving and machine learning, which also have quite some impact. But so given this experience, what would you see as Mark's law for us to understand reality?
I have no idea. Mark's law, acknowledge the structure. I don't know. That's an important thing, which sometimes I don't feel myself that my own research makes so much progress with that. But actually, I think this would be the most important thing. Acknowledge really the structure of the problems, and because, that's important.
Right. And last point. So 5 years from now, I'm going to come visit you wherever you are, maybe Stuttgart, and I'm going to confront you with a prediction you're going to make today. I'm going to say, look, Mark, you predicted to me today or 5 years back that the following would happen. Now, did it really come out like that? Was your prediction really supported? What's his prediction you would like to make today?
That you can test me in 5 years, right? Well, so our goal actually is, and I usually say to my students in 5 years, as a point of motivation, and that we would have that robot that autonomously explores its environment and discovers all degrees of freedom. That sounds like a simple statement initially, but if you look around the room right now and think about all degrees of freedom in that room, kinematic ones, right? There's a lot. And in order to discover them, the robot would have to start pushing, kicking, letting fall, letting drop, everything, grasping all of these things and shake it and see if something moves. And that's something I would want
Great.
to
Okay, I'll come and see if the robot tore down your lab 5 years from now.
Yeah.
So Marc Toussaint, thank you very much for this conversation.
Welcome. Thank you.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.